Hey, so today I'm going to be going over breadth first search on a grid or a 2D matrix. And one of the reasons I think that this is a good first graph algorithm is because you can use it to traverse a graph and also find the minimum number of steps from one point to another with certain constraints on how you can traverse the graph. And also I think that the breadth first search introduces a couple key data structures. You can use maps and dictionaries because you have to check if something was visited. Then also you have to use a queue and understand the difference between a queue and a stack. So I think that depth first search and breadth first search are probably the two most important graph algorithms, especially when you're starting out with data structures. And personally, I prefer breadth first search. I think it's a little bit more useful, but maybe I just understand a little bit more, so I'm a little biased. But the idea here from this Advent of Code 2022 problem is we want to go from S to E, where E has the value of Z and S has the value of A. And we can't move more than one character numeric value up. So for example, B is one more than A, so we can go AB, but we can't go BQ. So if we were to look at the process of this, it would probably be something like this. Yeah, then we go V, WX, YZ. We would loop up around here until we get to E. And when you're doing breadth first search, you visit every adjacent node first, which is where the breadth component comes in. And here, I'll do a little demo of this, just so we can see exactly what it's happening, how it's going wide first, but then as it hits those walls where it can't traverse, it has to go back narrow, and it wraps around, going to every possible value it can until it returns the correct number of steps in the correct position to 5 for the character code of capital E. So here we'll go a little bit more into some of the details of breadth first search. So at its core, breadth first search is just checking every node one step away from the current node, and it creates this ripple-like effect through a graph. So I like to try to visualize certain algorithms, especially graph algorithms, and I just imagine it like dropping a rock or something into a body of water and seeing those ripples move out. And if you were to put certain barriers, the ripples would go around it, but then they would go wide again once they got past it. Whereas something like depth first search, I think of as lightning or an ant colony of these long tendrils going down, coming back up, and then extending back down again, where it seems much more precise and less broad than breadth first search. So some of the basic logic and some of the data structures we have to use. The first one being a map or a dictionary, depending on what your language calls it. So we have the visited data structure, that's what we'll call it, and we want to save the node somehow, some unique identifier to the node that we're at. And if we're just traversing, we'll store booleans to see if it's been visited, but if we're counting steps, we'll have this step from the origin, or from the node one step before, plus 1. And then we use a queue to store the nodes that need to be visited. And we do this because a queue is first in, first out. And that's opposed to a stack, which is last in, first out. So using a queue ensures that all nodes one node away from the current node will be processed first. And by first, I mean before any nodes that are 2 units away from the current node. And this is the breadth component of the search. So we exhaust all adjacent nodes before moving deeper into the graph. So when we're checking with this map data structure, we just want to see if there's a nil value for that node, or whatever is nil in the language that you're using. And if it is, that means it hasn't been visited, and then we can add that to the queue, and we repeat this for all nodes adjacent to the current one. And we repeat this until our desired end value is found or the entire graph has been traversed. So complete traversal occurs when the queue is completely empty. So why did I choose TypeScript versus JavaScript or a node-based language in the first place? And the main reason is the types. I'm decent with JavaScript, been using it for a while, but never really delved into TypeScript too much, so I got the, what's it called? Effective TypeScript book. Just read through it, really liked it, never really saw the need for it, but after using it, I can definitely see how it helps JavaScript code bases. And JavaScript does a little bit of weird stuff. It's passed by reference for arrays and objects. So just kind of ensuring that the grid can't change using read-only properties. I just wanted to kind of add these guardrails even if they weren't needed, and really quote-unquote like purify or make the program very safe. And the reason I wanted to use a node language is because console.table, and it allows for really good animations. And lastly, it took me way too long to realize I needed to use spread notation to get the value at the front of the queue. I'm sure there's an append function that I could have used, but I just was using push, I believe, and I was like losing my mind why it wasn't working, why it was finding the value, but the number of steps was way too high. So first step is to create the types. And this is the TypeScript specific aspect, not necessarily the algorithmic aspect. So we have the character code for start, the character code for end. We have the read-only matrix, ensuring that it doesn't get altered. And then we have the input string, which we convert to this matrix 2D. And then we have the interface position, which is the row and column of the current value in the graph, or the grid in this case. Now we have the function itself. So we take the start position, we take the grid, and we want to return a number. And this number is the number of steps to get to E from S, if we can. We have the queue, which is an array of positions. And we have visited, which is a map that takes a string and a number. And I believe in JavaScript you have to take a string as the key value in a map, or at least you can't use integers. I made that mistake as well, and it cost me a couple hours when I was attempting this in just pure JavaScript. So we push the start value into the queue, and then we use string interpolation to create unique keys to each position. And we set the start value to 0 because the start is 0 steps away from itself. And then while the queue has nodes in it, while there's unvisited nodes, we keep this loop going. We pop off a value from the queue, and we set that as our current position. We make our custom current key, and then we use whatever function you have for this specific graph, the bounds of what values can be accessed from which values. In this case, it's making sure that the value is not off the grid, and making sure that the value is not more than one numerical value higher. And then once we have these moves, we'll use the for of syntax in TypeScript to get all the position M values, and we get that custom key, and then we check if it's been seen. If it hasn't been seen, we append 1 to the current value for the new move from the current value. And what this ensures is that we find the minimum distance from one point to another, in this case S to E, because we check every adjacent node first. So we can tell exactly how many steps it is from S to E. And then if we find that N value, what we do is we just log out the position, and then we return the key in visited, which is going to be equal to the one before it plus 1, which is the distance to that end value. And here's the part that I kept messing up at, where I just used the spread notation to make it very obvious that this is first in, first out, because we're popping that off immediately, but we're also adding it to the front. And then if we haven't reached the end, we just return -1. So that's the algorithm and part of the TypeScript stuff that I used for it. I hope that helps. If I made any mistakes or you have any questions, just shoot me a message in the comments. Thanks.